some sense that if it wasn't for those things, that price spike would have been much, much bigger. So supply and demand are very, very steep, very inelastic. Okay, so now with that background in mind, let's think about what's going to happen or what might happen with climate change on U.S. crop yields. Okay, the early projections were pretty optimistic overall, 10, 15 years ago. Mostly optimistic mainly because of a large positive influence of CO2 fertilization that they saw in greenhouse experiments. 50% increases in yield were projected in some cases. Massive. Also, longer growing seasons in the northern regions. They thought, well, maybe this will be really good. We can grow a lot more in places like Wisconsin and Minnesota. Modest temperatures were expected from excess heat in more southern areas. Today, a lot less optimism about the effects of CO2 fertilization, because instead of doing things in the greenhouse, they do field experiments, and things look a lot more complicated. And I know I'm not the expert here, but a lot of the stuff coming out now is there's a lot less confident that CO2 will be much of a boost at all. And second, there's a lot more pessimism about the effects of extreme heat. And it's probably drought, but there's also possibly other effects of extreme heat on growth. So, what seems pretty clear when you're looking at agricultural effects is that extremes matter the most. Okay? Not too cold, not too hot, not too wet, not too dry. How will climate change affect the frequency of extremes? Well, it's probably going to increase them. If there's some sort of threshold effect and the distribution shifts just a little bit, the frequency of the threshold or the extreme events could double easily or triple, or actually by our measure can go up tenfold pretty easily. So what we kind of recognize, and we're kind of good number crunchers, we're not really plant scientists and that use these simulation models. We really wanted to look at the data. We're pretty good at crunching numbers. So what we recognize is that you really need fine-scale data. You need to measure everything that's going on with temperatures to really measure this. You need to account for all the variations within a day and across all days in a growing season. And mostly people were just, when they're doing statistical analysis, looking at averages. And averages really obscure the extremes. So we did a lot of work trying to make the best data possible. This audience probably isn't too interested in the details. Very quickly, we basically used all the weather station data that's out there, and we also used this monthly climate data that comes out of this climate model, PRISM, which climate scientists say is the best out there. And we combined these two using, well, a lot of programming. And I can talk to you about the details if you're interested. To basically approximate on a very fine grid over the entire country the weather on a daily time scale on a 4-kilometer grid. So it's a massive, massive data set. It goes all the way back to 1950. And now, and for Indiana, there's enough weather stations in Indiana that we were able to go back to the beginning of the century. So we did a little bit of extended analysis there. Okay, so the other thing we need to do is not average over location. So we want to match the weather to where the crops are actually grown as precisely as possible. And then we've got satellite data that tells where the crops are grown. This kind of shows, if you zoom in on this, you can see the grid that we've got, and you can see where the crops are grown. The darker pixels are more cropland. So we put all this into a model that really accounts for the time at each degree. Partial days, actually we do this kind of continuously at each degree, and incorporating this into a regression model, a statistical model, we can predict yields much, much better than anyone else has been able to do before. And what we found by kind of estimating this thing in a very flexible way, I'm actually showing you 3 models here, is that temperatures are really good and improve yield up to around 30 degrees Celsius, so the optimal temperatures in the mid to upper 80s. But above that, things get really bad really fast. Really bad, so you get this downward spike. And I'm showing you 3 models, like kind of a flexible, smooth model, this step function, and then there's this piecewise linear model, which can turn into something very simple in the statistical analysis. Now this measure right here, I'm going to refer to, which really captures that, is degree days above 29 degrees Celsius, sometimes 30 degrees Celsius. So this is a key measure, and it really captures this. And actually, I can explain about 70% of the typical deviation from trend in the aggregate yield for the United States using that one measure. And this down here shows you the histogram of the frequency of temperatures. So what's going to happen with climate change is the frequency of that thing's going to move up, and you're going to get a lot more in this bad area, which doesn't seem like such a good thing. We looked at this for soybeans. We get the same pattern. We looked at it for cotton. We got the same pattern. We tried to look at it for wheat. We don't get the same pattern. Wheat's a lot more complicated. We haven't figured that out yet. But for these crops, which are the 3 most valuable crops in the United States, we get this pretty clear standard relationship. And it predicts much better. And these are out-of-sample predictions. So we eliminate a particular year from the data. We estimate the model using other years, and then we predict for the out-of-sample year. And we do this for all possible combinations of years. And we put it up against other models, again using I think our better data, but we still beat the other models by a pretty good margin, 30 to 50% better. Okay, put this in perspective. Here's Indiana. I'm going to look at the long run, and we've got, what I'm showing here is just that key measure. And this is just the deviation from the average degree days above 29 degrees Celsius. So this key measure, this is in Indiana. It's centered at 0, which is the average, and then you get variations. And what's interesting, I don't have the plot here, but these variations match yields in Indiana really, really well. And these little bar plots here, this kind of shows the spread across different counties within Indiana. We didn't have county level data back here, so there's just one dot. But the major droughts really show up really well. And this is where things were really, really bad. So this is, I guess, our own drought measure is degree days above 29 degrees Celsius. It really predicts yields well. So this line right here, which you can maybe barely see, and I'm going to highlight it a little bit better, that's the predicted increase with the slow warming scenario for the average between 2017 and 2099. That would be, on average, Indiana is going to be far worse than it was during the Dust Bowl years, where yields really got hammered. Okay, so that seems like a pretty big deal. That's under the slow warming scenario. The fast warming scenario would be up near the ceiling somewhere. Okay, crop sensitivity to extreme heat. What we can do is we can look at this basic sensitivity to extreme heat, and we allowed that to vary smoothly over time in Indiana. We really wanted to look at Indiana because we had a longer history. And we wanted to see what was going on with adoption of hybrid corn. And because of adoption of hybrid corn happened right after the Dust Bowl. It happened during a really hot time. And we didn't see in our early analysis, we saw the sensitivity very stable over time and over space, and different ways of identifying this. We looked at this data lots of ways. Very stable relationship. And we found when we looked earlier on that we did see an increase in heat tolerance. This is kind of measuring heat tolerance with different models. And we did see an increase in heat tolerance with the adoption of hybrid corn. But beginning around 1960 with the adoption of single cross hybrids, it's really declined. And today, it looks as sensitive to extreme heat as ever before. Okay. And it's been a bad thing throughout. Okay. So, now if we just take our model and make projections, now these are big caveats, I believe. We're not taking into account CO2 fertilization, and we're not taking into account changing growing areas, which are going to change probably in a big way. We're going to grow different crops in different areas. There's just no way to get around that kind of draw that conclusion. Impact for 2020 to 2049 for corn, relative to the status quo of historical temperatures, minus over 20% for corn under the slow warming scenario, up to nearly 30% in the fastest business as usual. That's just 2020 to 2049. Slightly less impacts for soybeans, and around the same for cotton and soybeans, but more uncertainty. And for 2070 to 2099, under the slow warming scenario, this is us